So this is work done by my former master's student. She's joining as a PhD student, Afia. So she has done all the heavy lifting, and I'm just here to present her work. I believe she's also online in case there is any question to answer the questions. Okay. So we are talking about one of the risks of using machine learning models in distribution system operation, and that is like the possibility of essentially attacking that model. So in this case, we are looking at a specific type of adversarial attack where the attacker adds a little bit of noise to the data. So the result of a state estimation could change drastically. So this is the type of attack that we are studying in this paper. So before I get to this attack, let me tell you a little bit about distribution system state estimation. So state estimation is the problem of estimating the unobserved variables in the distribution system from the observed variables. So you have some information, you want to estimate the value of the ones that you do not observe. And then the data that's usually used for state estimation is the meter data, either smart meter data or perhaps synchrophasor data, PMU data. They will be collected and then used to solve this problem. The state that we want to estimate is perhaps voltage magnitude or phase angle. Okay, so what are the conventional state estimation techniques? So this is based on weighted least square or weighted least squares. And since this is a nonlinear model, people normally use iterative methods like the Gauss-Newton method to solve this problem. But this is done in most cases for the transmission system. For distribution system, there are lots of issues with using like conventional methods. For this reason, there are other approaches that are data-driven state estimation techniques, and they're using just some neural networks to perform this state estimation. It's just a mapping from observed data to unobserved data. So they're preferred in distribution systems for various reasons. They are usually providing better accuracy. There is no convergence issue, and they're faster to use than solving the weighted least squares problem using the Gauss-Newton method. So now conventional methods are found vulnerable to various types of false data injection attacks that are designed to bypass bad data detection mechanisms that we have. But the question is that now we have this new class of distribution system state estimation techniques. Are they also vulnerable or perhaps robust to these data manipulation attacks? So that's the question we study in this paper. So there is a little bit of work in this area in the past. In fact, there are papers that studied FDIA, false data injection attack. So this is the conventional approach to attack distribution system state estimation. And then we had like a paper last year in E-Energy that we studied adversarial attacks against distribution system state estimation. And there's another paper in this area as well. All of these are studying a specific class of attacks called on-target attacks. So what is an on-targeted attack? An on-targeted attack is the one where there is no adversarial target, meaning that you are not attacking the model to cause overestimation or perhaps underestimation. The effect of this attack on the state estimation result is completely random, right? So this is called an on-targeted attack. The other form of attack is targeted attack, where you want to cause, for example, overestimation in all cases, right? So this is a more serious type of attack because it can have consequences for system operation. So we started with 3 research questions. The first one is that we want to assess the vulnerability of these data-driven DSSC methods to traditional targeted FDIAs. Then the same thing, but this time for targeted adversarial attacks. And again, we are talking about a specific type of attack called evasion attack that I will introduce in the next few slides. And finally, we want to see what access privileges are required to generate the attack vector. So in order to study these research questions, we used special type of data-driven state estimation model that is based on an ensemble of resonant models. So when you use ensemble learning, you usually have better robustness. And this is shown in previous work in this area. And that's why we chose this model, because we wanted to see if this model that is usually claimed to be more robust to these attacks, is it really robust to target attacks or not? So that's the logic. So this is a model that uses 3 base learners. The base learners in this case are resonant networks with 13 dense layers. And then we have a multivariate linear regressor that is used as the meta learner. And then the special adversarial target that we use in this case is causing overestimation of node voltages. So the first attack is the targeted version of the false data injection attack. The attack is very simple. So you have the attack vector called X, the state which is called X sub t. So this is a state at time t. And then you want to see how to essentially change the measurements, which is Z sub t, the measurement at time t. So we are adding some attack vector A to Z sub t to create essentially what's called Z adversarial sub t. And then this will essentially change the state. So it will change the state from X sub t to X adversarial sub t. And in this case, the attack vector can be calculated if you have access to the H matrix. H matrix is a system measurement matrix that is normally used in model-based state estimation. So a very simple attack, and it's a target attack because if you want to change the state by C, you know how much you have to change, how much in fact you have to add to your measurement, which is A. So you can specify the magnitude of change and the direction of change. That's why it's a targeted attack. So that's just giving an example where the C vector is calculated as you see in this slide. Okay, so the requirement is access to the H matrix. And then what we did is that we tried to see if our data-driven state estimation technique is indeed robust to this attack. So what you see on this slide is the distribution of measured bus voltage magnitude ratio, which is the estimated voltage over the true voltage value. So this is on the x-axis. One means that they are the same. And then the frequency of data points that we have on the y-axis. So as you see here, the targeted FDIA, when it's performed against a weighted least square state estimation technique, which is a conventional state estimation technique, it in fact moves the state in a certain direction, right? It only causes over estimation of voltage, which is expected. But then when you perform this attack against a data-driven state estimation attack, a state estimation model, the impact of this attack is kind of random. Sometimes it causes overestimation, sometimes it causes underestimation, right? So this is because the data-driven DSSE model does not really rely on the H matrix, right? And it's kind of what we expected. Now, the more interesting one is when we try to assess the vulnerability to targeted adversarial attacks. So I'm going to show you a specific type of adversarial attack called fast gradient sign method. This is originally proposed against classification models. So you have some input image, you want to add a little bit of noise to this input image such that you completely change the result of the classification model. So instead of, for example, classifying panda, it classifies something else, for example, tiger, right? So now we use the same idea, but this time we try to attack a regression problem rather than a classification model. So it's a regression model in this case. So what does it do? So we have a victim model, that's the DSSE model that is used for state estimation, data-driven DSSE model. And then we have the surrogate model. This is a model that the attacker can learn from the input and output of the state estimation problem, right? And it might be completely different from the victim model. So it's just a model that the attacker learns. And this is the basic FGSM attack. Note that here we are taking the gradient of the loss, which is L, with respect to the input, which is X, not with respect to theta, the parameter of the model. So when you want to train the model, we normally take the gradient with respect to theta. In this case, in order to generate the attack, we are taking the gradient with respect to X. Right? And then we change, or we essentially move our data point in that direction. We take the sign of that and then multiply that by epsilon, and that gives us the attack vector. So the targeted version of this attack uses a very simple idea. Instead of taking the gradient with respect to X, when X is just the true state, let's replace the true state with the state that you want this to, in fact, estimate. And if you want to cause over voltage, then pick state value that is close to 1.05. This will cause over voltage, right? So if you compare the two equations for the attack vector, they're almost identical. The only difference is that when you calculate the loss is calculated between the output of the model and then the target state rather than the true state, right? So we just replace this with the target state. And the target state is randomly picked between these two bounds that you see there, right? So they are very close to 1.05, causing over voltage. So this is the attack idea. We looked at this in two settings, white box setting and black box setting. In the white box setting, we assume that the attacker knows exactly the model, right? So the surrogate model is exactly the same as the victim model. In the black box setting, the attacker learns a different model, and it's a different model as you see here. Okay, so the result is what you see here, and it looks like that this attack is only successful in the white box setting, meaning that knowing the state estimation model that is used by the system operator is crucial for performing this attack. And if you do not have this information, you cannot essentially move this, the system state in the direction that you want it. It will have some random impact. So that's it for the third question. Very quickly, what access is required for this attack? So obviously read and write access to measurement data in order to perform this attack. And apart from this, we need complete knowledge of the victim DSSE model because it's only successful in the white box setting. So the three takeaways. What we found is that traditional targeted FDIA does not work against data-driven DSSE methods. But the data-driven DSSE methods are vulnerable to the targeted adversarial attacks only in the white box setting. And now the open questions are, first, can we design, in fact, targeted adversarial attacks that are also successful in the black box setting? So that's the first question. And the second question is that, can we use feature saliency map that is normally used to detect adversarial attacks to also detect this particular type of attack? And with that, I will conclude my talk and take questions. Thank you.